Fundamental technology. 2. Sealing. Fundamentals of sealing technology and key considerations in engine development. In engine development, sealing technology is a critical factor that directly influences both performance and durability. Even a minor sealing failure can lead to oil or coolant leakage, which may result in decreased engine performance or even severe breakdowns. Furthermore, leakage of combustion gases has a direct impact on compliance with environmental regulations and exhaust emission performance. For this reason, the design, manufacturing, and assembly of seals are unavoidable and essential themes for every engineer. This video outlines key design considerations for representative sealing methods, namely O-rings, liquid gaskets, and metallic gaskets. O-rings. The fundamental principle when selecting an O-ring is, choose the largest cross-section that space allows. A larger cross-section ensures stable deformation under load and enables long-term sealing performance. Two critical design parameters are compression ratio and filling factor. Compression ratio. If the compression ratio is excessive, the O-ring will suffer from compression set, lose elasticity, and fail to maintain proper sealing. Generally, a compression ratio of 20–30% at the tolerance midpoint is recommended. Filling factor. The volumetric ratio of the O-ring to the groove must also be considered. If the O-ring volume is too large relative to the groove, deformation becomes uncontrollable. If too small, sealing force becomes insufficient. A filling factor of approximately 75% at the tolerance midpoint is ideal. Proper balance between these factors must be ensured during the design phase. From the perspective of assembly, face seals are preferable to radial seals whenever possible, since they are easier to handle and improve both manufacturability and serviceability. This is especially advantageous in automotive engines, where mass production and maintenance are fundamental requirements. For O-rings used in face sealing, the design must ensure reliable contact at either the inner or outer diameter, preventing extrusion or displacement under pressure. Although circular cross-sections are standard, elliptical shapes can also be applied when necessary, provided the O-ring remains securely seated within the groove. Material selection is equally crucial. Engine seals are exposed to oil, coolant, and combustion gases, across temperatures ranging from ambient to several hundred degrees Celsius. While NBR, nitrile rubber, is widely used, FKM, fluoroelastomer, or silicone rubber is preferred in high-temperature applications. For fuel system seals, resistance to fuel and low permeability are mandatory, as incorrect material selection can result in hardening, swelling, and premature leakage. Designers must carefully consider working fluid, temperature range, and pressure conditions to select the most suitable material. Liquid gaskets. Liquid gaskets cure through reaction with atmospheric moisture. In deep grooves, curing may be delayed, reducing sealing effectiveness. Therefore, groove design should ensure that sufficient gasket material remains on the surface, and that any excess material adheres firmly to mating parts. Detached cured fragments can circulate within the medium and cause unexpected malfunctions. Despite these challenges, liquid gaskets are highly effective in filling microscopic surface roughness, making them suitable for complex geometries and thin-walled components. As such, their application should be determined on a case-by-case basis. Metallic gaskets and V-clamps. In exhaust systems and combustion chamber areas, metallic gaskets and V-clamp seals are commonly used. Rubber-based seals cannot withstand the extreme temperature and pressure conditions in these regions. Metallic gaskets provide rigidity and heat resistance, often featuring surface elastic coatings, in order that gas tightness can be improved. V-clamps distribute uniform clamping load across the joint, delivering excellent sealing performance. These solutions are not limited to automotive internal combustion engines but are also widely applied in aerospace engines and industrial turbines, where operating environments are extremely severe. Since the development of seals used in exhaust systems is technically challenging, it is common practice to have specialized manufacturers handle the design and production. Conclusion. Key considerations in sealing design for engines include proper O-ring cross-section and compression ratio, appropriate groove geometry and filling factor, material selection matched to operating fluids and conditions, assembly considerations to prevent displacement or extrusion, use of metallic gaskets in high temperature, high pressure regions. Seal failures are often rooted in oversights during the design stage. Therefore, combining simulation with experimental validation from the early phases is essential to deriving optimal specifications. With appropriate selection and design of sealing elements, engine reliability and long-term durability can be significantly enhanced.